So this lecture will continue on. We've developed the linear angular momentum equation for fluids. In this lecture, we'll develop the angular momentum equation for fluids. So in some cases, it's necessary to obtain the torque produced by flow. This typically occurs when analyzing turbo machinery, having blades that rotate about a fixed axis, such as pumps, turbines, fans, and compressors. So it'd be a case you'd have water flow impinging on a propeller. The water is imparting a energy to make the blades turn. And so what's really happening is you have, similar to throwing a baseball and hitting this and making it turn, you have a conservation of momentum, but instead of a baseball, you're hitting it with a fluid. So again, we're going to treat this, since we're dealing with water flow, as a control volume kind of problem. So here, you have to look at the control volume. And so here, the angular momentum is R cross MV typically. So here's your origin. So here's R to the center of the control volume. Here's the direction along a streamline, MV. So you're going to have this cross product term that we'll have to deal with. So in general, again, you can break up the angular momentum equation into two parts. A part that deals with the control volume and a part that deals with the control surfaces. Now, if we consider steady flow, the first term on the right will be zero, since there will be no local change of angular momentum inside the control volume. So the only thing we'll have to worry about in this case is what goes through the control surfaces. Also, for an ideal fluid, which has a constant density and uniform velocity through the open control surfaces, we can integrate out this second term, and we can write this equation much simpler, like as shown in the equation below. And again, the best way to look at this, how to solve this, is in a practical example. So let's look at example 6.7. Here we have water flowing out of the port of a fire hydrant. We want to determine the reactions at the fixed support necessary to hold the symmetric 60-pound fire hydrant in place. So he gives us a little schematic. The water comes into the fire hydrant. It has a 6-inch diameter. Going out of the fire hydrant has a 4-inch diameter. And we'll consider our control volume to be the part in red here. And it's 2 feet from A to B. So this is the case of steady flow. So we can use the much simpler angular momentum equation. The water is going to be assumed to be an ideal fluid. So the gamma for water is 62.4 pounds per cubic feet. Now in this kind of problem, we're going to start and we're going to apply all the different equations we've learned. So first of all, we can look at the continuity equation. Q equals V times A, and since we know what the Q value is, we were told in the problems, and we know the diameters of A and B, we can calculate V of A and V of B. We can also look at the Bernoulli's equation from A to B. We can write our terms on both sides of the equation. The pressure at B is going to be 0, since that's where the water comes out. The velocity at B we calculated. ZB is 2 feet. It's given in the problem. Z of A is 0, because that's our reference levels down here at the bottom of at A. The pressure at A, we don't know. That's what we're trying to find. V at A, we know what that value is there, so we can find the pressure at A. 533.2 pounds per square foot. So now we can apply the linear momentum equation. So we write down the equation itself. Again, we have two terms, a control volume term and a control surface term. The control volume term is 0. And the control surface term, we again end up with two terms that we're kind of familiar with at this point. VB, and then there's a density velocity area plus VA, density velocity area. And again, I've explained the negative sign here, so I won't repeat myself. So this equation is inherently a three-dimensional equation. This is a two-dimensional problem in the x and y direction. So let's look at this equation in the x direction. So what forces are in the x direction? That's just our f of x. Uh, Looking at this equation, um, all of this is in the x direction at b, and none of this has a component in the x direction. So here we repeat this term here, and this one is 0 because that's all in the y direction. So we can plug in our values. We know what VB is because we calculated it from the previous slide. Density, velocity, area we can calculate because the area at B, it's 2 inches, so we can convert it to feet, pi r squared. Finally, we can calculate f of x, 88.8 pounds. So we can repeat our calculation in the y direction. So again, looking at this equation, on the left-hand side, what forces do we have? Well, we have the force F of y that's we are saying is downward here. We also have the weight of the fire hydrant itself, which we're told is a 60-pound fire hydrant. We also have the pressure that's pushing up on it. So here we found the pressure pushing at P of A was 533.2 pounds per square feet. So we'll have the pressure times the area at A. Again, it's a 3-inch radius at A. So pressure times area, that's a force, minus F of Y, that's the force we're trying to find, the support force. And then we can't forget the weight of the fire hydrant, which is 60 pounds. So there's 3 forces on it. Now on the right-hand side, again, we got the velocity at A, which we found up here. This is the density, the velocity at A, and again, the area. So the only unknown is F of Y, which is 84.2 pounds. So finally, we can apply the angular momentum equation about point A here. So we eliminate the force reactions at this point here. So we have the general equation we showed in the first couple of slides. So the R cross V, so R is the distance from here to there, so it's 2 feet. And then we'll have the R times V of B term, and this is R is up and V is this way, so it's R cross V is 90 degrees. So sine of 90 is 1, so we don't really have an angle here. The density VB times area at B. So we can plug those quantities in. We can calculate that the moment is 178 pound foot at A. It's what we found here. All right, that's the end of this lecture. I'll see you in the next lecture.